Shaped by the universe, beyond the geometry of reality. Introduction: the geometry of existence. Geometry governs the universe, shaping not only the physical laws that hold everything together, but also the evolution of life and civilizations. On Earth, we are accustomed to living on a spherical planet, where gravity, ecosystems, and human societies have developed in harmony with the forces dictated by this shape. This familiar geometry creates predictable systems, flowing rivers, weather patterns, and gravitational stability that have allowed life to flourish. But what if the world wasn't spherical? What if we lived on a cube, a pyramid, or a torus? How would these altered geometries redefine our understanding of existence? The purpose of this book is to embark on an imaginative journey into the realms of shaped universes. We will explore how the fundamental laws of motion, thermodynamics, electromagnetism, and even time itself behave in worlds of different geometrical forms. These thought experiments challenge not only our scientific assumptions, but also our philosophical understanding of reality. Geometry and the laws of nature. Each shape presents a new lens through which to examine the behavior of natural laws. The spherical Earth has been the basis of much of our understanding of physics and cosmology, but what happens when this foundation is altered? For example, in a cubical universe, the gravitational forces at the edges and corners would warp, creating extreme environmental conditions. Meanwhile, in a toroidal world, gravity would pull toward a central ring, disrupting the flow of water and air, and challenging the way civilizations would develop transportation and infrastructure. These shaped universes force us to reconsider key principles, such as Newton's laws of motion, the behavior of entropy in thermodynamic systems, and the very nature of space-time. By examining these different geometries, we learn how deeply geometry influences not just physical systems, but the very possibility of life and civilization. Scientific thought experiments. The exploration of these shaped worlds serves as more than mere speculation. It serves as a way to push the boundaries of theoretical physics, mathematics, and cosmology. Thought experiments have always played a crucial role in scientific discovery. Just as Einstein used the thought experiment of riding on a beam of light to develop the theory of relativity, we will use the imaginative exercise of exploring different geometric worlds to deepen our understanding of physical laws. In a pyramidal universe, the weakening of gravity as you ascend to the apex creates challenges for life at higher altitudes. Civilizations in such a world may need to develop technologies that counteract the effects of vertical gravitational variations, such as advanced methods of energy transfer or specialized transportation systems. The philosophical implications of geometry. Beyond the scientific consequences, geometry also holds philosophical significance. The shape of a world may shape the minds of its inhabitants. In a fractal universe, where patterns repeat endlessly at every scale, societies might view existence as inherently interconnected, with no clear boundary between the small and the large. Such a worldview challenges our human-centric perspective on individuality and hierarchy, encouraging new ways of thinking about unity, order, and chaos. Similarly, in a hyperbolic universe, the vastness of space and the distortion of distances might lead its inhabitants to a philosophy of existential isolation, where the infinite stretches of space reflect the unfathomable nature of reality itself. Would time in such a universe behave differently? Could such civilizations ever develop a coherent sense of history, or would they live in a perpetual state of exploration with no final destination? The role of imagination in scientific inquiry. Imagination plays a vital role in expanding the horizons of human knowledge. The worlds we are about to explore are not confined to the realm of fantasy. They serve as tools for questioning the assumptions we hold about the universe. By considering worlds shaped like cubes, pyramids, tori fractals, and more, we open the door to new perspectives on physics, cosmology, and the nature of life itself. This book seeks to merge the power of scientific reasoning with the boundless potential of the human imagination. As we journey through these shaped universes, we will not only explore the mechanics of how such worlds might work, but also consider the broader philosophical and existential questions they raise. A journey into the unknown. The journey ahead is as much a voyage into the unknown as it is a scientific and philosophical exploration. We will begin by examining the spherical world we know so well, using it as a baseline for comparison. From there, we will venture into uncharted territory, exploring the cubical, pyramidal, cylindrical, toroidal, fractal, and hyperbolic universes. Through this journey, we hope to gain new insights into the relationship between geometry, physics, and existence itself. As we contemplate the infinite possibilities of shaped universes, we invite you to stretch your imagination, challenge your assumptions, and embrace the complexity and wonder of the cosmos. Chapter 1. The Spherical Universe. The spherical world, like Earth, is the foundation of much of our understanding of the universe. Its shape creates uniform gravitational forces, supports stable ecosystems, and allows life to flourish. The familiar behaviors of water flow, weather patterns, and the distribution of natural resources are all deeply tied to the planet's geometry. But why is the spherical shape so common in celestial bodies, and how does it influence the physical laws that govern the world? Newton's laws of motion on a spherical planet. In a spherical world, Newton's laws of motion apply in familiar ways. Gravity pulls evenly toward the center, creating predictable conditions for motion and stability across the planet's surface. First law, inertia. An object at rest remains at rest, and an object in motion stays in motion unless acted upon by an external force. The uniform gravitational field of a spherical world ensures that this law remains consistent everywhere on the planet. Objects behave predictably, with minimal interference from gravitational anomalies. Second law, F equals ma. Force equals mass times acceleration. On a spherical planet, the gravitational force is uniformly directed toward the center, resulting in stable acceleration due to gravity. This uniformity allows for consistent motion, be it the flow of rivers down mountain slopes or the predictable trajectories of projectiles. Third law, action-reaction. For every action, there is an equal and opposite reaction. In a spherical environment, this holds true in a balanced way. When a boat pushes through the water pushes back with equal force, enabling efficient transportation. This law also underlies the balance of forces in natural systems, such as the interaction between ocean currents and atmospheric pressure, gravitational symmetry, and orbital mechanics. The spherical shape of celestial bodies, including planets and stars, is a direct result of gravity. Gravity pulls matter inward equally from all directions, creating the most energy-efficient shape, a sphere. This symmetry allows for stable orbits, whether it's the moon around the Earth or the Earth around the sun. In a spherical world, these orbits follow predictable paths governed by Kepler's laws of planetary motion. Elliptical orbits form due to gravitational pull, and the distances between celestial bodies remain relatively constant, ensuring consistent environmental conditions like day length, seasons, and climate. This predictability is crucial for the development of life, as it provides a stable, nurturing environment where organisms can evolve and thrive. Thermodynamics on a spherical planet. The laws of thermodynamics play out in familiar ways on a spherical planet, with the planet's shape supporting energy distribution that fosters stable climates and ecosystems. First law, conservation of energy. Energy is neither created nor destroyed, but it can change forms. On a spherical planet like Earth, solar energy drives the global climate system, with heat being absorbed and redistributed through ocean currents, atmospheric winds, and radiative balance. The planet's round shape ensures that energy is distributed relatively evenly, preventing extreme temperature variations that would make life difficult. Second law, entropy. In energy transfers, the total disorder of a system can only increase. The spherical geometry facilitates the even spread of energy, allowing for relatively stable weather systems and the flow of heat from equatorial regions to the poles. The result is the gradual entropy increase that we see in the Earth's natural cycles, from the slow decay of organic matter to the cooling of volcanic lava. Third law, absolute zero. As a system's temperature approaches absolute zero, entropy approaches a constant minimum. In the coldest regions of the planet, such as the poles, this law plays out as temperatures near absolute zero, and heat transfer slows to a halt. The spherical nature of the planet allows such cold regions to exist while still supporting life in other areas, thanks to the even distribution of solar radiation. Effects on water flow, climate, and civilization. The spherical shape of a planet has a profound effect on natural systems, particularly water flow and climate. On Earth, rivers follow the curvature of the land, flowing from high-altitude regions toward the seas. This predictable pattern of water movement has shaped the development of human civilizations, with major cities and agricultural systems springing up along riverbanks and coasts. Water flow and ecosystems. In a spherical world, gravity pulls water toward the planet's center, creating predictable river systems and ocean currents. The flow of water is vital for sustaining life, as it distributes nutrients, supports agriculture, and serves as a means of transportation. Civilizations have historically thrived along rivers due to their reliability as sources of water, food, and transportation. Mountains and climate. The atmosphere wraps around a spherical planet in a way that creates stable pressure systems and predictable weather patterns. Mountains act as natural barriers, influencing airflow and precipitation. As air rises over mountains, it cools and condenses, forming clouds and rain on the windward side. The leeward side, in contrast, often experiences drier, desert-like conditions. This geographic diversity has led to the rise of different types of societies, from riverine agricultural communities to nomadic desert tribes. Philosophical reflections. Stability, balance, and linear progression. Living on a spherical planet fosters a sense of balance and continuity in human thought. The regularity of day and night, the changing seasons, and the predictable cycles of nature give rise to a linear understanding of time and progress. Civilizations on a spherical world tend to develop philosophies and religions that emphasize order, harmony, and the cyclical renewal of life. In many ways, the geometry of Earth has influenced the way humans perceive the world. Our linear progression through time, from birth to death, mirrors the stable orbit of the Earth around the Sun. Similarly, the balance of natural forces, such as the cycles of life and death, growth and decay, reflects the symmetry and stability of the spherical shape. Religions that arise on a spherical planet often incorporate symbols of balance and wholeness, such as circles and spheres, which represent unity and completeness. Philosophical systems, too, may emphasize the interconnectedness of all things, much like the interconnected systems of the planet's biosphere. Real-world comparisons and insights. The spherical world we inhabit is not just a theoretical construct. It's a real, living system that we interact with every day. By understanding how physical laws operate in this familiar setting, we can better appreciate the unique challenges and opportunities that arise in other geometric worlds. The stability and predictability of a spherical planet provide a valuable contrast to the more chaotic environments of cubical or hyperbolic worlds. In these alternative universes, the familiar laws of physics would behave in dramatically different ways, forcing civilizations to adapt to ever-shifting environments. But for now, Earth remains our model of a balanced, stable world, one where the harmony of nature is reflected in both its physical laws and its philosophical outlooks. Chapter 2. The Cubical Universe. In a cubical world, the regular gravitational forces we take for granted in a spherical world no longer apply uniformly. Instead, the cubical shape introduces unique challenges, particularly at the edges and corners of the cube, where gravitational forces become distorted and unpredictable. These distortions create extreme environmental conditions, forcing life and civilizations to adapt in ways that differ drastically from the stability we know on Earth. Newton's laws of motion in a cubical universe. Newton's laws of motion still hold in the cubical world, but their behavior is altered by the non-uniform gravitational field that emerges from the cube's shape. First law, inertia. On the flat faces of the cube, objects behave similarly to how they do on Earth. However, as objects move toward the edges or corners, gravitational anomalies cause sudden shifts in motion. The cube's sharp corners and edges make movement near these areas more erratic, and inertia becomes harder to maintain due to changes in gravitational force. Second law, F equals ma, the cube's uneven gravitational distribution creates varying forces. For example, in the center of each face, gravity acts similarly to Earth's gravity, providing predictable acceleration. But as one moves closer to an edge or corner, the gravitational pull becomes weaker, causing deceleration and shifts in the object's trajectory. This uneven force distribution challenges the construction of infrastructure, travel routes, and even how life evolves on the cube's surface. Third law, action-reaction. For every action, there is an equal and opposite reaction. However, near the cube's edges and corners, where gravitational forces fluctuate, these reactions can be less predictable. Movement and force transfer in these regions could lead to unexpected outcomes as the gravitational vectors change between the cube's flat faces and its sharp boundaries. Gravitational anomalies and environmental effects. One of the most significant differences between a cubical and a spherical world lies in how gravity behaves across the surface. On Earth, gravity pulls equally toward the center, creating a stable, uniform environment. In contrast, a cubical planet has stronger gravitational forces at the center of each face and much weaker forces near the edges and corners. The center of each face acts as the most hospitable region on the cube. Here, gravity behaves much like it does on Earth, pulling objects straight down toward the center of the planet. These central areas are where civilizations would most likely develop, as they offer the most stable conditions for agriculture, transportation, and habitation. As one approaches the edges and corners of the cube, the gravitational pull weakens, creating harsh, unpredictable environments. Near the corners, gravity could become so weak that objects might float or experience irregular motion, making these areas nearly uninhabitable. The edges, though less extreme than the corners, still pose challenges. Civilizations living near the edges would need to adapt to weaker gravity and potentially dangerous environmental conditions, such as sudden drops in air pressure and temperature. Thermodynamics and energy distribution on a cube. The shape of the cube also affects how energy is distributed, particularly in terms of heat transfer and atmospheric behavior. First law, conservation of energy. Energy remains conserved in a cubical world, but heat distribution across the planet is uneven. The flat faces of the cube absorb and retain heat more effectively, creating warmer climates in these areas. In contrast, the edges and corners tend to lose heat quickly, resulting in cold, barren regions. This imbalance could lead to significant temperature gradients, with the central faces experiencing temperate climates and the edges resembling polar conditions. Second law, entropy. The increase of entropy, or disorder, is more pronounced in the cube's harsh regions. The differences in temperature and energy distribution between the faces, edges, and corners create local systems with varying levels of order and chaos. For instance, the central regions of the faces may have more organized, stable climates, while the corners could be chaotic and hostile to life. Third law, absolute zero. In the coldest corners of the cubical planet, where energy dissipates rapidly, temperatures could approach absolute zero, rendering these areas uninhabitable. These corners might become desolate, icy wastelands with little to no potential for life. Effects on water flow, climate, and civilization. The cubical shape radically alters the flow of water and the behavior of the atmosphere. On Earth, water naturally flows downhill toward large bodies of water, creating predictable river systems and ocean currents. However, in a cubical world, the gravitational anomalies at the edges and corners create challenges for water flow and climate. Water on a cubical planet would pool at the center of each face, forming large seas or lakes. From these central water bodies, rivers would flow outward toward the edges. However, near the edges and corners, the weakened gravitational pull could cause water to stagnate or evaporate, leading to arid, desert-like conditions. Civilizations would develop around these central water sources, much like cities form around rivers and lakes on Earth. Tectonic activity on a cubical planet would likely concentrate in the center of each face, where gravitational forces are strongest. Mountains might form here, but would become less common as one moves toward the edges. The atmosphere, too, would be denser at the center of each face, supporting rich ecosystems and stable weather patterns. Near the edges, the thinning atmosphere would create colder, drier climates, with less potential for large-scale life. Human settlements on a cubical world would likely cluster around the central bodies of water on each face. The stable gravitational forces and moderate climates in these areas would provide the best conditions for agriculture, trade, and technological development. However, travel across the edges and corners would pose significant challenges, requiring advanced technology to navigate the unpredictable gravitational and environmental conditions. Philosophical reflections. Hierarchy, boundaries, and survival. The cubical world, with its sharp edges and hierarchical distribution of environmental conditions, may give rise to unique philosophical and societal structures. Inhabitants of a cubical world may view the edges and corners as symbolic boundaries, separating the known, stable regions from the chaotic, inhospitable zones. This division could lead to a philosophy centered around boundaries and limits, where the edges of the cube represent the edges of knowledge, or the boundary between civilization and the unknown. Social hierarchies could develop based on proximity to the center of each face. Those living in the central, stable regions might be considered privileged, while those near the edges and corners might be seen as more rugged or daring, yet marginalized. This physical stratification could mirror societal divisions, creating cultures that emphasize survival and adaptation in the face of extreme conditions. The philosophical significance of the cube's shape may also extend to how time and progress are perceived. In contrast to the continuous, cyclical nature of time on a spherical planet, a cubical world might foster a more segmented view of history and progress. Each face could be seen as its own contained world with its own history, disconnected from the other faces except at the edges, where contact between civilizations is difficult. Technological innovations for a cubical world. The unique challenges of living on a cubical planet would drive technological innovations. In particular, the development of transportation systems capable of navigating the gravitational anomalies at the edges and corners would be critical for trade and communication between different regions. Advanced transportation technologies such as anti-gravity vehicles or flying machines would be necessary to travel between the faces of the cube. These systems would allow for the safe movement of goods and people across the cube's dangerous edges. Trade routes would likely connect the central regions of each face, but would avoid the more hazardous corners and edges. The uneven distribution of heat and energy would encourage the development of localized energy systems that take advantage of the unique conditions on each face. Solar energy could be harnessed more effectively in the warm central regions, while advanced geothermal or nuclear energy systems might be necessary in the colder, more extreme environments near the edges and corners. Chapter 3. The Pyramidal Universe. The pyramidal world presents a unique vertical differentiation in both gravity and environmental conditions. Life is concentrated at the base of the pyramid, where gravity is strongest and the atmosphere is thickest, supporting more stable climates and ecosystems. As one ascends the pyramid, the gravitational pull weakens, and conditions become harsher, with thinner air and extreme temperatures. This vertical gradient shapes not only the planet's natural environment, but also the civilizations that arise on its surface. Newton's laws of motion in a pyramidal universe. In the pyramidal world, Newton's laws of motion still hold true, but the way these laws manifest changes with altitude. First law, inertia. At the base of the pyramid where gravity is strongest, objects behave similarly to how they do on Earth. However, as objects move upward toward the apex, where gravitational pull weakens, inertia becomes more difficult to maintain. Near the top of the pyramid, objects may move with less resistance, even appearing to float, due to the reduced gravitational forces. Second law, FMA. Force and acceleration behave normally at lower altitudes, but near the top of the pyramid, where gravity weakens, objects require less force to accelerate. This results in slower acceleration and deceleration, which would challenge transportation and the movement of goods at higher altitudes. Third law, action-reaction. For every action, there is an equal and opposite reaction. This remains true, but the intensity of these reactions decreases near the apex, where gravity has less influence. At the base, natural forces such as wind or the flow of water behave predictably, but at higher altitudes, the forces involved may be weaker and less reliable. Gravitational variations and environmental effects. The pyramidal world is defined by its vertical gravitational gradient. Gravity is strongest at the base of the pyramid and weakest at the apex, creating distinct environmental zones. At the base of the pyramid, where gravity is strongest, the atmosphere is thick and conducive to life. The strong gravitational pull keeps air, water, and ecosystems in place, supporting agriculture and human settlements. The base is likely to be the most densely populated region, with abundant natural resources and fertile land. As one ascends the pyramid, gravity weakens and the atmosphere becomes thinner. At mid-levels, ecosystems become less diverse and the climate grows colder. Rivers and lakes are less common, as water struggles to flow in regions with lower gravitational forces. Human settlements at these altitudes would need to adapt to harsher living conditions with limited access to natural resources and agricultural land. At the apex, gravity is so weak that objects may float or move with little effort. The air is thin and temperatures near absolute zero make the apex uninhabitable for most life forms. The apex, therefore, is likely to be a barren, cold region, possibly used only for scientific research or spiritual purposes. Thermodynamics and energy distribution. The vertical gradient in gravity also affects how energy is distributed on a pyramidal planet. Heat, water, and energy behave differently at various altitudes, creating distinct climate zones. First law, conservation of energy. Energy is conserved, but the vertical structure of the pyramid causes uneven energy distribution. The base retains more heat, creating a warmer, more habitable environment. The middle and upper regions lose heat quickly, leading to colder climates with less potential for life. Second law, entropy. Entropy increases predictably, but the vertical gradient in energy distribution leads to more ordered conditions at the base, where the climate is stable. Higher up, where the environment is colder and less hospitable, the system becomes more chaotic, with rapidly changing weather patterns and fluctuating temperatures. Third law, absolute zero. As temperatures approach absolute zero, entropy reaches its minimum. At the apex of the pyramid, where heat dissipates quickly and gravitational forces are weak, temperatures may drop near absolute zero, making the uppermost levels almost entirely uninhabitable. Effects on water flow, climate, and civilization. Water flows differently on a pyramidal planet. Instead of flowing from high-altitude regions toward the sea as on Earth, water flows from the apex of the pyramid down its sloped sides. Rivers and waterfalls cascade down the pyramid, gathering into lakes and seas at the base. At the base of the pyramid, the abundance of water and fertile land supports agriculture and large human populations. Civilizations in this region thrive as they have access to plentiful resources, stable climates, and navigable rivers. The base is likely to be the political, economic, and cultural center of the planet, with the majority of the population living here. As one moves higher up the pyramid, water becomes scarcer and the climate grows colder. Mid-level regions may rely on advanced engineering to channel water from the apex to sustain their populations. Agricultural practices would need to adapt to the cooler climate, with hardier crops and technologies that conserve water and energy. At the apex, the cold, barren landscape makes it difficult for civilizations to develop. However, the spiritual or symbolic significance of the apex may lead to its use for religious or ceremonial purposes. The top of the pyramid could be a place of pilgrimage reserved for elites or spiritual leaders who ascend the pyramid to connect with the divine. Philosophical reflections. Verticality, hierarchy, and spiritual ascent. The pyramidal world's vertical structure naturally gives rise to a hierarchical society. The physical journey from the base to the apex mirrors the social and political structures that emerge on such a planet. Those who live at the base handle agriculture, trade, and labor, while those in the middle tiers may hold administrative or military positions. At the apex reside the elite or spiritual leaders, occupying the most sacred and revered space. This social hierarchy is reinforced by the pyramid's geometry. The journey to the apex becomes a metaphor for spiritual ascent, with the most powerful or enlightened individuals residing closest to the heavens. Philosophical and religious beliefs on a pyramidal world would likely emphasize concepts of hierarchy, order, and the pursuit of higher knowledge. Ascension, both physical and spiritual, may be seen as the ultimate goal, with individuals striving to rise through the ranks of society or attain enlightenment. The verticality of the pyramidal world may also shape its inhabitants' view of time and progress. Instead of a cyclical view of time, as might be seen in a toroidal universe, the pyramidal world's inhabitants may view time as a linear journey toward a higher state of being. Progress is not simply a return to earlier states, but a continuous climb toward a higher purpose. Technological innovations for a pyramidal world. The unique challenges of life on a pyramidal planet would lead to technological innovations focused on vertical transportation, energy distribution, and survival in harsh climates. Vertical transportation. The steep slopes of the pyramid require advanced vertical transportation systems, such as elevators, stairways, or flying vehicles. These technologies would allow for the movement of people and goods between the base, mid-levels, and apex. Civilizations at the base may rely on these systems to transport goods from higher altitudes, while those near the apex may use them to gather resources from the base. Water and energy systems. Water from the apex would need to be channeled down through a series of aqueducts, pipes, or artificial rivers to sustain populations at the base and mid-levels. Similarly, energy generated at the base may need to be distributed upward, while colder regions may rely on alternative energy sources such as geothermal power or nuclear reactors. Architecture and engineering. Civilizations in the pyramidal world would need to develop advanced architectural techniques to build structures on the pyramid's steep slopes. Cities may be terraced, with buildings constructed into the sides of the pyramid, or they may rely on floating platforms and towers that rise vertically. Chapter 4. The cylindrical universe. In a cylindrical world, the geometry of the planet stretches infinitely along its axis, creating unique environmental conditions where gravity pulls toward the central line of the cylinder. This shape causes significant differences in how life and civilizations evolve compared to a spherical or cubical world. Societies develop in long, continuous regions along the surface, and natural resources like water flow in patterns determined by the cylindrical shape. The cylindrical universe challenges our understanding of orbits, gravity, and resource distribution in ways that fundamentally reshape life as we know it. Newton's laws of motion in a cylindrical universe. On a cylindrical planet, Newton's laws of motion still apply, but the cylindrical shape introduces new dynamics in how these laws manifest. First law, inertia. Along the length of the cylinder, objects in motion behave predictably, similar to how they do on Earth. However, as objects move away from the central axis of the cylinder, the gravitational pull weakens, creating lighter environments toward the edges of the cylindrical surface. This weakening of gravity leads to unusual motion near the outer edges, where objects feel less resistance and can move more freely. Second law, F equals mem. Force and acceleration remain consistent along the central axis of the cylinder, allowing for stable transportation and infrastructure development. However, as one approaches the edges of the cylindrical world, the weakening gravitational force reduces acceleration, resulting in low-gravity environments where even small forces can cause significant movement. Third law, action-reaction. For every action, there is an equal and opposite reaction. This remains true throughout the cylindrical world, but the cylindrical shape may cause unexpected interactions as forces propagate along the curved surface. In the central regions, forces behave predictably, but near the edges, the weakening of gravity leads to more erratic reactions, particularly in mechanical systems. Gravitational effects and environmental conditions. The cylindrical world's unique gravitational distribution creates distinct environmental conditions across the surface. Gravity pulls inward toward the central axis, meaning that areas closest to this axis experience gravity similar to Earth's, while areas farther from the axis, near the outer edges, experience weaker gravitational forces. The central axis is where life and civilization thrive along the central line of the cylinder, where gravitational forces are strongest and environmental conditions are stable. Here, ecosystems flourish, and societies can develop large-scale infrastructure, agriculture, and trade routes. The central regions are rich in natural resources with fertile land and access to stable water sources. The outer edges experience weaker gravitational forces as one moves away from the central axis toward the outer edges. These outer regions are characterized by lower air pressure, reduced atmospheric density, and colder temperatures. Life here would be sparse, and human settlements would need advanced technology to survive in the low-gravity, low-resource environment. The outer edges may resemble the conditions of Earth's high-altitude or polar regions, with harsh climates and extreme conditions. Thermodynamics and energy distribution in a cylindrical world. The cylindrical shape affects how energy is distributed across the planet, particularly in terms of heat transfer and atmospheric behavior. First law, conservation of energy. Energy is conserved, but the cylindrical shape creates variations in heat distribution. The central axis retains more heat, supporting warm climates and stable ecosystems. Toward the outer edges, heat dissipates more quickly, leading to colder, more barren environments. This uneven energy distribution creates distinct climate zones along the length and breadth of the cylinder. Second law, entropy. Entropy increases predictably, but the cylindrical shape allows for more efficient energy transfer along the central axis. In contrast, the outer edges experience greater disorder, with erratic weather patterns and fluctuating temperatures. The result is a world where the central regions are stable and predictable, while the outer edges are chaotic and difficult to inhabit. Third law, absolute zero. As temperatures near absolute zero, entropy approaches a constant minimum. The outermost regions of the cylindrical world, far from the central axis, may experience near-freezing temperatures due to the rapid dissipation of heat. These cold, barren regions are inhospitable to most forms of life and would likely remain uninhabited. Effects on water flow, climate, and civilization. Water behaves differently on a cylindrical planet compared to a spherical world. Instead of flowing toward a central point like an ocean, water on a cylindrical planet flows along the length of the cylinder, forming long rivers that stretch for thousands of kilometers. Water flow and ecosystems. Rivers on a cylindrical planet follow the curvature of the surface, flowing in long, continuous streams from one end of the cylinder to the other. These rivers provide a constant source of water for agriculture and human settlements, allowing civilizations to flourish along their banks. However, the outer regions of the cylinder, far from the central axis, may be dry and barren due to the lack of water flow and weaker gravitational forces. Mountains and atmosphere. The atmosphere is thickest along the central axis of the cylinder, where gravitational forces hold it in place. This supports rich ecosystems and stable weather patterns similar to those found on Earth. However, as one moves toward the outer edges, the atmosphere thins out, creating drier, colder conditions. Mountains may form along the length of the cylinder, but they are less common near the outer edges, where gravitational forces are weaker and tectonic activity is less pronounced. Civilization. Human civilizations would develop primarily along the central axis of the cylindrical world, where conditions are most hospitable. Cities and agricultural zones would follow the flow of the rivers, forming long, continuous societies that stretch for thousands of kilometers. These linear societies would be interconnected by trade routes and transportation networks that follow the natural contours of the cylinder. The outer regions, with their harsh climates and low gravity, would be sparsely populated, with only the most technologically advanced civilizations able to survive in these extreme environments. Philosophical reflections, continuity, time, and linear progression. The cylindrical world's shape influences not only the physical environment, but also the way its inhabitants perceive time, space, and progress. Unlike the circular, closed loops of a toroidal or spherical world, the cylindrical world offers an infinite stretch along its axis. This linearity may shape the way its inhabitants think about time and history, viewing them as continuous, unbroken processes rather than cyclical patterns. Inhabitants of a cylindrical world may develop a philosophy that emphasizes linear progression, continuity, and the pursuit of endless growth. Time could be seen as a straight path with no beginning or end, mirroring the infinite stretch of the cylindrical surface. Progress would be viewed as a continuous journey, with civilizations striving to expand further along the length of the cylinder, pushing the boundaries of exploration and knowledge. This sense of linearity might also extend to the social and political structures of the cylindrical world. Societies could be organized in a hierarchical manner, with power concentrated along the central axis, where conditions are most stable and diminishing toward the outer edges. The farther one moves from the central regions, the more isolated and rugged life becomes, reflecting the challenges of survival in a harsh, low-gravity environment. Technological innovations for a cylindrical world. The unique challenges of life on a cylindrical planet would inspire technological advancements in transportation, energy generation, and communication. Long-distance transportation. Given the vast distances along the length of the cylinder, civilizations would need efficient long-distance transportation systems. High-speed trains or flying vehicles could travel the length of the cylinder, connecting distant cities and agricultural hubs. These transportation systems would need to be adapted to the cylindrical curvature, ensuring stability and safety in both high-gravity and low-gravity regions. Energy systems. The cylindrical world's shape would allow for the efficient generation and distribution of energy. Hydroelectric power from the long, continuous rivers could provide a reliable source of energy, while wind and solar power could be harnessed along the central axis, where conditions are most stable. Advanced energy storage systems would be necessary to ensure a steady supply of power in the more remote, low-gravity regions. Communication networks. Communication in a cylindrical world would require a robust network of satellites or ground-based relay stations to ensure that signals can travel across vast distances. The natural curvature of the cylinder may cause signal disruptions in low-gravity areas, requiring specialized technologies to maintain reliable communication between the central and outer regions. Chapter 5. The Toroidal Universe. A toroidal universe, shaped like a donut or ring, introduces unique gravitational and environmental challenges. The toroidal shape, with a central hole and curved surface, significantly alters how gravity, energy, and matter interact. Life in this universe would be shaped by the peculiarities of the torus's geometry, where gravity pulls toward the central ring, and civilizations may face a complex relationship with time, space, and energy flow. The toroidal universe offers a fascinating exploration of how non-Euclidean geometry impacts the development of life, technology, and philosophical thought. Newton's laws of motion in a toroidal universe. Newton's laws still hold in a toroidal universe, but the way forces interact across the curved surface is different from what we experience on Earth. First law, inertia. Along the outer ring of the torus, objects move predictably, similar to how they do on a spherical planet. However, as one moves toward the inner curve of the torus, gravitational forces weaken, and inertia becomes less consistent. Objects might float or experience unusual motion near the center of the ring, where gravity exerts less force. Second law, F equals ma. Force and acceleration behave normally on the outer regions of the torus, but near the inner ring, the weakened gravitational pull allows for faster accelerations with less applied force. This discrepancy could lead to a division in technological and transportation systems, where different parts of the torus require distinct approaches to movement and infrastructure. Third law, action-reaction. For every action, there is an equal and opposite reaction. This remains true throughout the torus, but the curvature of the surface complicates how forces are distributed. On the outer side, reactions are more predictable, while near the inner curve, forces may propagate in unexpected ways due to the shifting gravitational vectors. Gravitational and environmental effects. The toroidal shape profoundly influences the behavior of gravity and the distribution of matter. Gravity pulls toward the central ring, meaning that life would develop in a curved, circular environment. However, the gravitational strength varies across the surface, creating zones of high and low gravity. The outer ring experiences stronger gravity, much like Earth's surface. This region would be the most hospitable to life, with stable environments conducive to agriculture, infrastructure, and large human settlements. Civilizations would likely develop here, taking advantage of the strong gravitational pull and the ability to construct predictable cities and transportation systems. The inner curve has weaker gravity as one moves toward the inner curve of the torus, creating low-gravity environments where objects may float or drift. Life in these regions would face challenges, with ecosystems adapted to low gravity and human technology needing to account for the difficulty of movement. The inner regions may be sparsely populated, with advanced technology required to sustain life in such extreme conditions. The central hole experiences the weakest gravity, and space may appear to stretch infinitely. This region would be inhospitable to life due to the lack of gravity and the thin atmosphere. However, it could become a place of scientific exploration, where researchers study the unique physics of the toroidal universe. Thermodynamics and energy flow in a toroidal world. The curved nature of the torus impacts how energy flows and is distributed across the surface. Heat, light, and other forms of energy behave differently on a toroidal planet, creating distinct climate zones and energy dynamics. First law, conservation of energy. Energy is conserved, but its distribution across the torus is uneven. The outer ring retains heat more effectively, creating warmer climates, while the inner regions lose heat quickly, leading to colder temperatures. This energy imbalance could create diverse climates across the torus, with temperate zones near the outer ring and frozen or barren regions near the inner curve. Second law, entropy. Entropy increases predictably, but the toroidal shape creates areas of high and low disorder. The outer ring supports more ordered systems, with stable climates and ecosystems, while the inner regions experience more chaotic weather patterns and temperature fluctuations due to the weaker gravitational pull and rapid heat dissipation. Third law, absolute zero. In the coldest parts of the inner curve and central hole, temperatures may approach absolute zero, making these areas uninhabitable. These regions could be desolate, icy wastelands where energy is rapidly lost to the void of space. Effects on water flow, climate, and civilization. The toroidal shape dramatically affects the flow of water and the distribution of climate zones. Water behaves differently on a toroidal planet compared to spherical worlds, following the curvature of the surface. Water flow and ecosystems. Water on a toroidal planet would pool along the outer ring, forming oceans, lakes, and rivers that follow the curved surface. These water bodies would create fertile regions along the outer edges, supporting diverse ecosystems and thriving human civilizations. However, as water flows toward the inner curve, it would struggle to move due to the weaker gravitational forces. These inner regions may experience droughts or desert-like conditions where water is scarce and life is sparse. Mountains and atmosphere. The atmosphere wraps around the torus, with thicker air concentrated near the outer ring. This region would experience stable weather patterns, supporting agriculture and human habitation. However, near the inner curve, the atmosphere would thin out, creating colder, windier conditions. Mountains may form along the outer edges of the torus, while the inner regions remain flat and barren, with few natural barriers to break the wind or shield against harsh climates. Civilization. Human civilizations would likely concentrate along the outer ring, where gravitational forces and environmental conditions are most favorable. These regions would develop into bustling cities, trade hubs, and agricultural centers. However, advanced technology would be necessary to explore and inhabit the inner curve, where the low-gravity environment and extreme climate make survival difficult. The central hole, with its lack of gravity and atmosphere, may become a place of mystery or spiritual significance, perhaps serving as a pilgrimage site or a location for scientific research. Philosophical reflections. Cyclic time and infinite loops. The toroidal shape of the universe naturally lends itself to philosophical interpretations about the nature of time and existence. Unlike spherical or cubical worlds, where time might be seen as linear or hierarchical, the toroidal world presents a vision of cyclic time and infinite loops. Inhabitants of a toroidal world may view time as circular, with no beginning or end, mirroring the unbroken loop of the torus's shape. Philosophical systems in such a world might emphasize the recurrence of events, the eternal return, and the cyclical nature of life, death, and rebirth. Time might be perceived not as a straight line, but as a continuous cycle, where civilizations rise, fall, and rise again in an endless loop. The central hole of the torus could take on symbolic meaning, representing a void or emptiness that sits at the center of existence. Philosophers might interpret this void as the unknown, the unknowable, or even a gateway to other dimensions or realities. In this way, the toroidal world offers a rich framework for exploring the philosophical implications of circularity, time, and the nature of reality. Technological innovations for a toroidal world. The unique shape of a toroidal planet would inspire technological advancements in areas such as transportation, energy generation, and resource management. Transportation systems. Given the curved nature of the torus, transportation systems would need to account for variations in gravity and terrain. High-speed trains or hovercraft could travel along the outer ring, connecting distant cities and agricultural zones. In the low-gravity inner regions, specialized vehicles capable of navigating the weaker gravitational pull would be necessary. potentially relying on advanced propulsion systems to counteract the lack of resistance. Energy systems. The toroidal shape would lend itself to innovative energy generation techniques. Solar energy could be harnessed along the outer ring, where sunlight is more consistent, while wind and geothermal energy could be harvested in the inner regions. Advanced energy storage systems would be required to manage the uneven distribution of power across the torus, ensuring a steady supply of energy for both the outer and inner regions. Climate control. The torus's uneven climate would inspire the development of technologies aimed at regulating temperature and weather patterns. Massive climate control systems capable of redirecting air and water flow might be deployed to stabilize regions near the inner curve, making them more habitable. These technologies would allow civilizations to expand beyond the outer ring, exploring and colonizing the more extreme environments of the toroidal world. Chapter 6. The Fractal Universe. A fractal universe is a world where patterns repeat themselves at every scale, creating a complex environment of endless self-similarity. Unlike a spherical or cubic universe where geometry is finite and predictable, a fractal world challenges our understanding of space, time, and reality. In such a universe, the boundaries between the large and the small, the simple and the complex, blur into one. This self-replicating geometry shapes not only the physical laws of the world, but also the evolution of life, technology, and civilization. Newton's laws of motion in a fractal universe. In a fractal universe, Newton's laws of motion still apply, but they operate in a vastly different context, where scales of size and distance lose their traditional meaning. First law, inertia. Objects in motion remain in motion, and objects at rest stay at rest, but the behavior of motion across different scales is complex. On a macro scale, inertia behaves predictably. However, as objects move between fractal layers, where similar structures repeat at different scales, their inertia may shift. For example, an object that appears large on one scale might behave as a small object on another, complicating motion and inertia as we understand them. Second law, Effelblum. The force required to move an object depends on its mass and acceleration, but in a fractal universe, mass is distributed across multiple scales. This means that an object's mass might appear different depending on the scale at which it is observed. As a result, force and acceleration behave in unexpected ways, where an object's movement can change dramatically as it moves between layers of the fractal structure. Third law, action-reaction. For every action, there is an equal and opposite reaction. This holds true in the fractal universe, but the propagation of forces is not straightforward. As forces interact across different scales, their effects ripple through the fractal structure in unpredictable ways, leading to complex reactions that can multiply or diminish depending on the scale at which they occur. Gravitational effects in a fractal world. Gravity in a fractal universe is not confined to a single scale, but operates at multiple levels of magnitude. This creates a unique gravitational field where gravity pulls objects towards similar fractal structures at various scales. At the large scale, gravity behaves predictably, pulling objects toward the largest visible fractal structures, much like Earth's gravity pulls objects toward its center. These large structures may appear as planetary-sized fractal formations, around which civilizations could develop. At the small scale, gravity continues to pull towards similar fractal formations. This means that within each large fractal structure, smaller substructures have their own gravitational fields, creating a universe of nested gravity wells. This complexity leads to a world where gravity can shift dramatically as one moves between scales, complicating navigation, transportation, and the flow of matter. Thermodynamics and energy distribution in a fractal world. The fractal structure of the universe also affects how energy is distributed and how thermodynamic laws operate. Energy moves differently in a world where space and matter are repeated across different scales, leading to unusual patterns of heat and energy flow. First law, conservation of energy. Energy is conserved across all scales, but the way it is transferred varies depending on the scale. In larger fractal structures, energy behaves predictably, moving from high-energy regions to low-energy regions. However, as energy moves between scales, it can dissipate or concentrate unpredictably, creating zones of intense heat or extreme cold within the same fractal environment. Second law, entropy. The increase of entropy or disorder is more complex in a fractal universe. The fractal structure creates pockets of low entropy where order persists across scales, and areas of high entropy where disorder reigns. These pockets of order and chaos interact with one another, creating a dynamic environment where localized order can give rise to complex, stable systems, while nearby regions experience chaos and rapid entropy increases. Third law, absolute zero. In the coldest regions of the fractal universe, temperatures approach absolute zero, but due to the fractal structure, these regions might exist at both the macro and micro scales. Large-scale voids of near-zero temperature may be found alongside tiny fractal substructures that retain heat. This uneven distribution of temperature further complicates life in the fractal universe. Effects on water flow, climate, and civilization. The self-similar nature of a fractal world alters the flow of natural resources, such as water, and creates complex ecosystems that mirror themselves at different scales. Civilization in a fractal universe would need to adapt to these unusual environmental patterns, developing technologies and social structures that reflect the complexity of their world. Water flow and ecosystems. In a fractal universe, water flows in repeating patterns across different scales. Large rivers may break into smaller tributaries, which then divide again into even smaller streams, each following the same fractal patterns. This means that water can be found flowing in predictable patterns at both the macro and micro scales, creating complex ecosystems that mirror one another across different layers of the fractal world. Civilizations would likely develop along these repeating water systems, using the predictability of fractal patterns to their advantage. However, the self-similar nature of the fractal universe means that resources could be concentrated in certain areas while remaining scarce in others. This uneven distribution of water and other natural resources could lead to competition between civilizations for control of the most fertile fractal zones. Mountains and atmosphere. The atmosphere in a fractal world behaves in similarly complex ways, with repeating patterns of air pressure, wind, and climate. Mountains may appear at both large and small scales, creating a nested system of mountain ranges that mirror one another across different levels of the fractal structure. This creates varied climates that repeat themselves, with similar weather patterns found in both large and small regions. Civilization. Human civilizations in a fractal world would need to develop technologies capable of navigating the complex geometry of their environment. Settlements might mirror the fractal pattern of the landscape, with cities and towns built to take advantage of the repeating natural features. These civilizations would likely develop highly specialized technologies to manipulate and control resources across multiple scales, allowing them to thrive in a world where size and distance are constantly shifting. Philosophical reflections, unity and interconnectedness. The fractal universe challenges traditional views of separation, hierarchy, and individuality. Inhabitants of a fractal world would likely develop philosophical systems that emphasize unity and interconnectedness, as the boundaries between the small and the large, the individual and the collective, blur into one. In a fractal world, the same patterns repeat themselves at every scale, creating a sense of unity between the macro and the micro. Philosophers in such a universe might view existence as inherently interconnected, with no clear distinction between the parts and the whole. This could give rise to a holistic worldview, where the individual is seen as a reflection of the larger universe, and vice versa. The self-similar nature of the fractal world might also inspire philosophical reflections on the nature of time and progress. Time may be seen not as a linear journey, but as a repeating cycle, where events and histories mirror themselves across different scales. Civilizations may view progress as a process of deepening understanding, rather than advancing toward a distant goal. In this way, the fractal universe invites its inhabitants to explore the interconnectedness of all things and the endless complexity of existence. Technological innovations for a fractal world. Living in a fractal universe would require advanced technologies capable of navigating the complexities of space, gravity, and energy at multiple scales. Transportation systems. In a fractal world, transportation would need to account for the shifting geometry of space. Vehicles may need to move seamlessly between different scales, shrinking or growing as they travel through the fractal landscape. Advanced propulsion systems could allow for rapid movement between fractal layers, enabling civilizations to explore the vast, self-replicating world around them. Energy systems. The fractal structure of the universe offers new possibilities for energy generation and storage. Civilizations might develop technologies that harness energy from different scales, capturing power from both large and small fractal structures. These energy systems would need to be adaptable, capable of shifting between scales to maximize efficiency and minimize waste. Architecture and engineering. Building structures in a fractal universe would require a deep understanding of the repeating patterns that define the landscape. Architects and engineers would design cities that mirror the fractal environment, constructing buildings that can adapt to the changing geometry of the world. These structures might need to grow or shrink to remain functional as the fractal pattern shifts, creating a dynamic, ever-changing built environment. Chapter 7. The Infinite Plane Universe. The infinite plane universe stretches endlessly in all directions, with no natural boundaries or edges. This universe defies the familiar concept of a finite, closed world, creating a fundamentally different relationship between gravity, space, and matter. Civilizations on an infinite plane experience unique environmental and philosophical challenges, as the horizon stretches infinitely and no natural curvature or end marks the boundary of their world. This flat, unbounded landscape fosters unique modes of existence, with infinite resources and limitless possibilities. Newton's laws of motion in an infinite plane universe. Newton's laws of motion still apply in an infinite plane universe, but they interact with the flat, infinite geometry in ways that differ from spherical or closed worlds. First law, inertia. Objects in motion remain in motion, and objects at rest stay at rest. In an infinite plane universe, this principle remains largely unchanged. However, the lack of any natural curvature or boundaries means that objects can move infinitely in a straight line without encountering any obstacles or edges. This creates the possibility of uninterrupted motion, where objects, once set in motion, can continue indefinitely. Second law, F equals ma. Force equals mass times acceleration, but in an infinite plane universe, the distribution of mass and force behaves differently due to the flat, unbounded nature of the plane. Large-scale forces, such as gravity, behave uniquely, pulling evenly across the entire plane. Objects experience uniform acceleration, but their trajectories can continue forever without any natural limit. Third law, action-reaction. For every action, there is an equal and opposite reaction. This remains true in the infinite plane universe, but the flat, unbounded landscape allows for more dispersed reactions. Without any natural barriers, forces can propagate infinitely across the plane, leading to extended chain reactions that spread out over vast distances. Gravitational and environmental effects. Gravity in an infinite plane universe does not pull toward a central point like it does in spherical worlds. Instead, it pulls evenly downward across the entire plane, creating a stable, uniform gravitational field. This uniformity results in a world where the horizon stretches endlessly in every direction, and the environment is relatively consistent across vast distances. The uniform gravity acts perpendicular to the surface of the plane, pulling downward with consistent force. This creates a stable environment where objects behave predictably, but the flatness of the plane means there is no central point of gravity. Instead of falling toward a specific center, objects are pulled straight down wherever they are on the plane. The endless horizons of the infinite plane mean there is no visible edge or curvature. The horizon stretches infinitely in all directions, creating a disorienting effect for inhabitants. Without natural boundaries or endpoints, civilizations must navigate a world where distances are potentially infinite, and the concept of far away loses its traditional meaning. Thermodynamics and energy distribution in an infinite plane. The infinite plane shape also affects how energy is distributed across the landscape. Without natural boundaries, energy behaves differently compared to a spherical or closed universe. First law, conservation of energy. Energy is still conserved, but its distribution across the plane is uniform and lacks the containment of a spherical world. Heat, for example, can dissipate infinitely across the plane, making localized energy concentration more difficult to achieve. Civilizations must develop advanced energy storage and generation systems to manage this dissipation. Second law, entropy. Entropy increases predictably, but the infinite nature of the plane creates an environment where disorder can spread endlessly. Without natural boundaries to contain or limit entropy, localized systems of order may exist, but they are constantly at risk of being overwhelmed by the vast, chaotic expanse of the infinite plane. Third law, absolute zero. In colder regions of the plane, temperatures may approach absolute zero. However, the infinite nature of the plane means that there are always regions farther away where energy can still exist, creating a dynamic balance between hot and cold regions. These extremes of temperature create diverse climates that civilizations must adapt to, with some regions becoming barren and frozen, while others remain habitable. Effects on water flow, climate, and civilization. Water behaves uniquely on an infinite plane, following the flat surface without any central body to flow toward. This creates sprawling rivers and oceans that extend indefinitely, while climate patterns spread endlessly across the plane. Water flow in ecosystems. On an infinite plane, water flows in predictable, flat patterns. Rivers stretch endlessly, with no central ocean or sea to flow into. Instead, water collects in massive, sprawling lakes and seas that have no natural end. These bodies of water provide vital resources for civilizations, but the infinite nature of the plane means that water is not contained in specific regions, allowing for potentially endless rivers and lakes that stretch as far as the eye can see. Mountains and atmosphere. The atmosphere in an infinite plane universe behaves similarly to Earth's, with air pressure and wind patterns following familiar principles. However, the lack of natural boundaries or curves means that weather patterns can continue indefinitely, creating large-scale climate zones that are consistent over vast distances. Mountains and hills form in the same way they do on Earth, but their scale and size can be immense, as there is no curvature to limit their growth. Civilization. Human civilizations on an infinite plane must adapt to a world where distances are infinite and horizons are boundless. Cities and settlements can spread endlessly with no natural limit to how far they can expand. Trade routes, communication networks, and transportation systems must be adapted to handle the vast, unbounded distances of the plane. This creates unique challenges for governance, resource management, and social organization, as traditional boundaries and borders become meaningless in a world without edges. Philosophical reflections, boundlessness, and infinite possibilities. The infinite nature of the plane universe naturally leads to philosophical questions about the nature of existence, boundaries, and possibility. Inhabitants of an infinite plane must grapple with the idea that their world has no end, no natural limits, and no inherent boundaries. In such a world, the concept of infinity becomes a central theme in philosophical and religious thought. Civilizations may view their existence as part of an endless, boundless reality, where progress and exploration have no final destination. The idea of reaching the end becomes meaningless, and instead inhabitants may focus on expanding their knowledge, resources, and understanding without ever expecting to find an ultimate limit. This infinite landscape could also lead to a sense of existential disorientation. Without natural boundaries or edges, individuals and societies may feel a sense of endlessness that challenges their sense of purpose and direction. Philosophers in an infinite plane universe may explore the meaning of existence in a world where there is always more to explore, more to discover, and no final point of arrival. Technological innovations for an infinite plane universe. The infinite nature of the plane creates unique technological challenges that civilizations must address to thrive in this boundless environment. Transportation systems. In a world without natural boundaries, transportation systems must be designed to handle vast distances. High-speed transportation networks capable of traversing thousands of kilometers would be essential for connecting distant cities and regions. Advanced propulsion systems, flying vehicles, or even teleportation technologies may be developed to allow civilizations to travel across the endless plane. Energy systems. The lack of natural boundaries also affects energy generation and distribution. Civilizations on the infinite plane would need to develop highly efficient energy systems capable of capturing and storing energy in a world where heat and power can dissipate endlessly. Solar, wind, and geothermal energy sources would be vital, along with advanced storage technologies to ensure a steady supply of power in remote regions of the plane. Communication networks. Communication over vast distances poses another challenge. Inhabitants of the infinite plane would need to develop robust communication networks, such as satellite systems or ground-based relays, to ensure that information can be transmitted across the endless landscape. These systems would need to be capable of handling the vast distances between cities and settlements, ensuring that even the most remote regions can stay connected. Chapter 8. The Holographic Universe. The concept of a holographic universe suggests that all the information that makes up our 3D reality is actually encoded on a 2D surface. This mind-bending idea reshapes our understanding of space, matter, and time. In such a universe, the boundary of reality is a 2-dimensional surface that projects a 3-dimensional world. The holographic principle has deep implications for the nature of existence, suggesting that the reality we experience may be a projection, not a fundamental aspect of the universe itself. Newton's laws of motion in a holographic universe. Newton's laws of motion still apply in a holographic universe, but the way objects behave is influenced by the idea that the universe's information is encoded on a 2-dimensional surface. First law, inertia. Objects in motion remain in motion, and objects at rest stay at rest. However, in a holographic universe, the motion of objects could be understood as a projection of the 2-dimensional data encoded at the universe's boundary. This means that inertia, while still consistent in our 3D experience, may originate from interactions that occur on a deeper 2-dimensional level. Second law, F equals ma. The force required to accelerate an object depends on its mass and the force applied, as in traditional Newtonian physics. However, in a holographic universe, the mass of objects might be a reflection of how much information is encoded about the object on the 2D surface. Therefore, changes in force and acceleration may correspond to alterations in the way the 2D surface encodes information. Third law, action-reaction. For every action, there is an equal and opposite reaction. This law still holds, but the origin of the forces could be traced back to the 2D encoding of the universe. As forces interact in the 3D projection, they might mirror deeper, underlying processes that are occurring in the 2-dimensional boundary layer. Gravitational and environmental effects. Gravity in a holographic universe remains a powerful force, but its origin may lie in the encoding of information on the universe's boundary. The way matter and energy behave in a holographic universe reveals the intricate connection between the 2D surface and the 3D experience. The holographic gravity suggests that gravitational forces in the 3D universe are a result of encoded information on the 2D boundary. Instead of thinking of gravity as purely a force that acts in 3D space, it can be seen as a projection of interactions on the 2D surface. This means that massive objects like planets and stars bend the fabric of space not only in 3D but also as part of their encoded data on the 2D layer. The environment as projection implies that every natural element we experience, from landscapes to weather patterns, is part of the 3D projection created by information on the 2D surface. As a result, the environment in a holographic universe might behave in ways that appear familiar, but are governed by deeper, unseen principles related to the encoding of the universe's boundary. Thermodynamics and energy distribution in a holographic world. The holographic principle also affects how energy is distributed and how thermodynamic laws operate in a universe that is fundamentally 2D but experienced in 3D. First law, conservation of energy. Energy is conserved, but the way it moves through the universe may be tied to how information is encoded on the 2D boundary. Energy transfer in the 3D world might reflect deeper patterns of information flow that occur on the 2D surface, meaning that energy distribution is not just a function of 3D space, but also of the structure of the encoded data. Second law, entropy. The increase of entropy, or disorder, may also relate to how information is distributed on the 2D boundary. In regions where the encoding of information is more disordered, the 3D projection might appear more chaotic. Conversely, regions where information is more structured might correspond to more ordered and predictable systems in the 3D world. Third law, absolute zero. As temperature approaches absolute zero, systems in the 3D world lose energy and approach a state of minimal entropy. However, in a holographic universe, this process might also reflect the cooling of the encoded information on the 2D surface. At absolute zero, the encoded data might be in its most stable, ordered state. Effects on water flow, climate, and civilization. In a holographic universe, even the flow of water and the climate itself are part of the 3D projection generated by the 2D boundary. Civilizations would experience familiar natural processes, but underlying these processes would be the 2D encoded information that governs their behavior. Water flow in ecosystems. The flow of water in rivers, lakes, and oceans would behave as expected in the 3D world, but the pathways water takes and the way it interacts with its environment may be linked to encoded patterns on the 2D boundary. Civilizations that develop near water would still rely on these resources, but they might come to understand that the availability and behavior of water are tied to deeper principles that govern the holographic nature of reality. Mountains and atmosphere. The atmosphere in a holographic universe appears to behave according to familiar principles, with air pressure, temperature, and wind patterns operating as we expect. However, these elements are still part of the projection from the 2D boundary. Mountains, hills, and other landforms, while solid in the 3D experience, are ultimately part of the encoded structure of the universe. Human civilizations would experience life much as they do in a non-holographic universe. However, advanced cultures might develop an understanding of the holographic principle, learning to manipulate the 2D encoded information to change or influence the 3D projection. This could lead to unprecedented control over the environment, technology, and even the fabric of reality itself. The ability to influence the underlying 2D layer could allow civilizations to reshape their surroundings or develop entirely new ways of interacting with the world. Philosophical reflections, reality, illusion, and the nature of existence. A holographic universe challenges deeply held beliefs about the nature of reality. If everything we experience in the 3D world is a projection of encoded data on a 2D surface, then the very nature of existence becomes a philosophical puzzle. Inhabitants of a holographic universe may develop philosophical systems that question the difference between reality and illusion. If the 3D world is merely a projection, then what is real? Philosophers might explore the idea that reality, as we experience it, is not the ultimate truth, but rather a constructed perception based on the underlying information encoded on the universe's boundary. This could lead to profound debates about the nature of existence, free will, and meaning. If everything is ultimately determined by the encoded information on the 2D surface, then how much control do individuals have over their lives? Is free will an illusion in a universe where reality itself is a projection? These questions would shape the philosophical and spiritual beliefs of civilizations in a holographic universe, leading to new ways of understanding purpose, identity, and the nature of being. Technological innovations for a holographic world. Living in a holographic universe would inspire technological advancements that reflect the deep connection between the 3D world and the underlying 2D surface. Holographic manipulation. Advanced civilizations may develop technologies capable of manipulating the encoded information on the 2D boundary. This could allow them to reshape the 3D projection, altering landscapes, materials, and even the laws of physics within the projected world. These technologies would give civilizations unprecedented control over their environment, allowing them to create new forms of matter, energy, and even life. Energy systems. In a holographic universe, energy systems may tap directly into the 2D surface, drawing power from the encoded information that governs the 3D projection. By accessing this deeper layer, civilizations could develop highly efficient energy systems that bypass the limitations of traditional power generation, allowing them to harness energy from the very fabric of reality. Communication networks. Communication technologies in a holographic universe would also be influenced by the underlying 2D structure. civilizations might develop ways to send information directly through the 2D surface, allowing for instantaneous communication across vast distances. This would revolutionize how societies interact, making it possible to communicate instantly with distant parts of the universe by transmitting messages through the encoded data that underlies the 3D world. Chapter 9. The Flatland Universe. A flatland universe is one where only two spatial dimensions exist. Length and width define this world, but there is no depth, height, or third dimension. Such a universe drastically changes how matter, life, and civilizations evolve. Without the third dimension, concepts like gravity, movement, and even identity are redefined. The constraints of a two-dimensional world present unique challenges and perspectives that fundamentally differ from those of a three-dimensional universe. Newton's laws of motion in a flatland universe. Newton's laws still apply, but they manifest differently in a two-dimensional plane, where the absence of depth changes the behavior of motion, force, and interaction. First law, inertia. In a flatland universe, objects still remain in motion or at rest unless acted upon by an external force. However, without the third dimension, objects can only move in two directions, and the plane itself imposes limits on the complexity of motion. The absence of vertical movement simplifies inertia, as all motion happens on a flat plane, with no up or down. Second law, effectivement. Force and acceleration operate as expected in two dimensions, but the absence of height changes how force is applied. In a flatland world, forces only act horizontally, which restricts the range of possible interactions. Objects move by being pushed or pulled along the surface, with no possibility of vertical lifts or drops. This makes transportation and engineering simpler, but limits the complexity of structures and machines. Third law, action-reaction. Every action still produces an equal and opposite reaction, but in a flatland universe, these reactions are confined to two dimensions. Collisions, forces, and interactions happen along lines or edges rather than in three-dimensional space. The consequences of motion and force are therefore easier to predict, but also less dynamic, as no vertical movement can occur. Gravitational and environmental effects. Gravity behaves in fundamentally different ways in a two-dimensional world. In a three-dimensional universe, gravity pulls objects toward a central point, but in flatland, gravity would act along a single plane, pulling objects together within this confined space. The way matter behaves, forms, and interacts is dramatically altered by the absence of depth. Flat gravity. Gravity acts along the two-dimensional plane, pulling objects together horizontally. Inhabitants of a flatland universe would not experience downward force in the way three-dimensional beings do. Instead, they would only feel the effects of gravity across their flat world, which could lead to compression of matter along the surface, potentially causing matter to stretch or distort under the force of gravity. No verticality. In a flatland universe, the concept of verticality doesn't exist. Buildings, mountains, and even organisms would spread out horizontally rather than growing upward. This drastically changes how ecosystems and cities form. For instance, trees or plants would be forced to spread across the surface, unable to rise above the ground. Similarly, civilizations would need to adapt to a world where height and depth are meaningless. Thermodynamics and energy distribution in a flatland world. The lack of depth in a flatland universe affects how energy is distributed and how thermodynamic laws operate. The two-dimensional nature of the world limits how energy flows, making heat and other forms of energy behave differently than in a three-dimensional space. First law, conservation of energy. Energy is still conserved, but in a flatland universe, it can only move along the plane. Without vertical pathways, heat and energy spread only horizontally, which creates more uniform energy distribution. Civilizations in this world would need to find ways to efficiently generate and store energy within the constraints of the flatland. Second law, entropy. Entropy still increases, but the absence of verticality means that disorder spreads evenly across the plane. In a two-dimensional world, localized systems of order and chaos would exist, but their interactions are confined to the surface. This limits the complexity of entropy's increase, creating a world where the flow of energy is more predictable and less chaotic than in three-dimensional space. Third law, absolute zero. As temperature approaches absolute zero, systems lose energy and approach maximum order. In a flatland universe, this process happens more uniformly, as energy dissipation occurs solely across the plane. The closer regions get to absolute zero, the more ordered and simplified their structures become, with all motion confined to 2 dimensions. Effects on water flow, climate, and civilization. In a flatland universe, even natural processes like water flow and climate take on entirely new forms. Civilizations must adapt to an environment where everything exists in 2 dimensions, which limits the way ecosystems and weather systems evolve. Water flow and ecosystems. Water in a flatland universe spreads out across the plane, flowing in thin, flat rivers and lakes. The lack of depth means that water cannot pool into deep oceans or form tall waves. Instead, it forms wide, shallow bodies that cover the surface. Civilizations would build their cities along these flat rivers and lakes, but would have to contend with the fact that water cannot flow downward to form reservoirs or aquifers. Agriculture, in particular, would need to adapt to the limitations of flat water systems. Mountains and atmosphere. In a flatland universe, mountains would not rise above the surface. Instead, they would appear as ridges or elevated areas that extend horizontally across the landscape. Similarly, the atmosphere would be a flat, uniform layer that spreads across the plane, with no layers of different pressures or temperatures above or below the surface. This would result in more stable weather patterns, but also limit the diversity of climates that can exist. Civilization. Human civilizations in a flatland world would need to adapt to the constraints of living in 2 dimensions. Buildings would be flat structures that spread outward rather than upward. Roads, transportation systems, and cities would be limited to the surface, and technology would need to account for the fact that there is no 3rd dimension in which to move or build. Overcrowding could become a significant issue in this world as populations expand horizontally across the surface with no possibility of vertical growth. Philosophical reflections. Perception, identity, and space. Inhabitants of a flatland universe would experience reality in fundamentally different ways from those in a 3-dimensional world. Their perception of space, distance, and identity would be confined to 2 dimensions, which would lead to unique philosophical and existential questions. In such a world, the concept of individuality and space would be redefined. Inhabitants might not even be able to perceive the concept of a 3rd dimension, and their understanding of identity and existence would be based entirely on what can be experienced within 2 dimensions. Philosophers in a flatland universe might debate the existence of higher dimensions, theorizing about the possibility of unseen realms beyond their perception. The idea of a 3rd dimension might remain purely theoretical, much like how humans contemplate the existence of other dimensions or realities beyond their own. Flatland philosophers may also grapple with questions about purpose and meaning in a world that appears so constrained. In a universe where expansion is only possible in 2 directions, how would societies view progress, exploration, and growth? The limits of their reality might inspire deep philosophical reflections on what it means to exist in a world that seems finite, and yet still holds infinite possibilities for discovery within the constraints of the plane. Technological innovations for a flatland world. Civilizations in a flatland universe would need to develop technologies that reflect the limitations and possibilities of 2-dimensional space. Without a 3rd dimension, their advancements would focus on making the most of the horizontal plane. Flatland architecture and engineering. In a flatland world, buildings and infrastructure would need to be designed for horizontal expansion. Structures would need to stretch outward across the plane, utilizing space efficiently while contending with the lack of height. Engineering solutions might focus on creating sprawling, interconnected cities that are optimized for surface-level living. Transportation systems. In a 2-dimensional universe, transportation systems would be limited to surface travel. Vehicles, trains, and other forms of transport would move along the flat plane, with no option for vertical movement. Civilizations would need to develop efficient means of transportation that can cover long distances quickly while remaining confined to the surface. Energy and resources. Energy generation and resource extraction would also need to account for the limitations of 2-dimensional space. Solar energy, wind power, and other renewable sources would be vital for sustaining civilizations in flatland. as traditional forms of energy extraction like drilling or mining would not be possible in a two-dimensional world. Chapter 10: The Simulation Universe. The idea of a simulation universe suggests that everything we experience, the physical world, consciousness, and even the laws of physics, are all part of a sophisticated simulation run by advanced entities or systems. In this universe, reality itself is a program, governed by algorithms, codes, and computations. The concept raises profound questions about the nature of existence, free will, and the relationship between creator and creation. Living in a simulation challenges every assumption about what is real, and understanding this universe requires a fundamental shift in perspective. Newton's laws of motion in a simulation universe. In a simulation universe, Newton's laws still apply, but they are implemented as programmed rules within the simulation's framework. These laws, while consistent, might be subject to alterations or glitches based on the underlying code. First law, inertia. Objects remain in motion or at rest unless acted upon by an external force, but in a simulation, this behavior is dictated by algorithms. Inertia is not a fundamental property of matter, but rather a rule enforced by the program. If the simulation's code changes, so could the behavior of objects, leading to potential inconsistencies or anomalies. Second law, F equals ma, force equals mass times acceleration, but the way force, mass, and acceleration are calculated depends on the simulation's programming. In a perfectly designed simulation, these variables behave exactly as they would in a real universe. However, glitches or intentional changes in the code could result in variations in how force and acceleration interact. Third law, action-reaction. For every action, there is an equal and opposite reaction, but in a simulation, this principle is enforced by the program's logic. If the simulation's designers or overseers modify the rules, actions and reactions could behave unpredictably or even violate physical laws in unexpected ways. Gravitational and environmental effects. In a simulated universe, gravity and environmental conditions are part of the programming that governs the simulation. While they may behave as expected, these forces are ultimately under the control of the system running the simulation. Programmed gravity. Gravity in a simulation universe operates according to coded algorithms. Planets, stars, and galaxies move and interact based on the simulation's rules, but this behavior can be altered or suspended by the system. The simulation might even introduce variations in gravity as part of its design, creating regions with different gravitational laws for specific purposes. Environment as code. The environment in a simulation is a detailed, coded construct. Landscapes, climates, and ecosystems are generated by algorithms, which means they can be manipulated or changed by the system at will. Weather patterns, natural disasters, and even geological features like mountains or oceans could be reset, altered, or controlled by modifying the program. This leads to the possibility that some environmental changes experienced by inhabitants may not be natural, but are instead deliberate adjustments made by the simulation's creators. Thermodynamics and energy distribution in a simulated world. The laws of thermodynamics in a simulation are part of the programmed environment. Energy flow, heat transfer, and entropy are all calculated by the simulation's code, meaning that these processes can be controlled, suspended, or manipulated. First law, conservation of energy. In a simulation, energy conservation is a programmed rule rather than a fundamental law of nature. The simulation may conserve energy for the sake of realism, but it could also introduce scenarios where energy appears or disappears at will. This means that energy is only conserved as long as the program enforces it, and anomalies may occur if the code is altered or encounters a glitch. Second law, entropy. Entropy increases predictably in a simulated universe, but this is a function of the program's rules. If the simulation is designed to mimic a real universe, entropy would follow the same patterns, leading to increasing disorder over time. However, the simulation could also be reset or reversed, allowing for a reduction in entropy in ways that would be impossible in a real universe. Third law, absolute zero. In a simulated universe, the concept of absolute zero still applies, but it is determined by the program's logic. The simulation may create conditions where temperatures approach absolute zero, but the system could also impose limits or artificial conditions that prevent certain regions from reaching this state. The behavior of matter and energy near absolute zero might reflect the limitations or quirks of the simulation's design. Effects on water flow, climate, and civilization. In a simulation universe, natural processes like water flow and climate are part of the coded environment, which means they can be manipulated or altered by the system. Civilizations in this universe experience these processes as real, but they are ultimately controlled by the simulation's designers. Water flow in ecosystems. Water in a simulation behaves according to programmed rules. Rivers, oceans, and weather patterns are generated by algorithms, and while they appear natural, their behavior is determined by the simulation's logic. Civilizations may develop alongside rivers or coastal regions, but the behavior of these water systems could be altered or manipulated by the simulation. For example, a flood or drought might not be a natural event, but rather a change in the system's programming. Mountains and atmosphere. The atmosphere in a simulation universe is also part of the program, with air pressure, temperature, and weather patterns all dictated by the simulation's code. Mountains, valleys, and other geological features are generated as part of the simulation's environment. These features can be changed, reset, or adjusted based on the needs or goals of the simulation's designers. Inhabitants may experience seemingly natural environmental shifts, but these changes might reflect the simulation's evolution or updates, rather than natural processes. Civilization. Human civilizations in a simulation universe develop as they would in a real universe, but their history, culture, and progress are shaped by the simulation's constraints. Societies might advance technologically and socially, unaware that their entire existence is governed by an external system. However, anomalies or glitches in the simulation could create unexplained phenomena, prompting civilizations to question the nature of their reality. These glitches might appear as supernatural events, miracles, or even paranormal activity, all of which are the result of errors or changes in the simulation's code. Philosophical reflections. Reality, free will, and the nature of existence. Living in a simulation raises profound questions about the nature of reality, free will, and existence itself. If everything is part of a programmed system, what does that mean for individual autonomy and the meaning of life? Reality as code. Inhabitants of a simulation universe must grapple with the idea that their reality is not fundamental, but instead a construct. Philosophers in this universe may debate whether anything is truly real if it is all part of a simulation. This could lead to existential crises, as individuals question the authenticity of their experiences and relationships, knowing that everything they perceive is ultimately the result of a programmed system. Free will in a simulated world. The question of free will becomes particularly challenging in a simulation universe. If every action, thought, and decision is governed by code, do individuals truly have control over their lives? Philosophers might argue that free will is an illusion in such a universe, with every choice predetermined by the system's programming. Others may believe that, even in a simulation, individuals can exert some influence over their actions, creating the possibility of meaningful choice within the system's constraints. The nature of existence. Living in a simulation forces individuals to confront the nature of existence itself. What does it mean to exist in a world that is not real? Are the inhabitants of the simulation less significant or valuable because they are part of a program? Philosophers might explore these questions, leading to new ways of understanding purpose, meaning, and the nature of being. In a simulation universe, the boundaries between reality and illusion blur, making it difficult to determine what, if anything, is truly real. Technological innovations for a simulated world. Living in a simulation universe could inspire technological advancements that reflect the nature of the programmed environment. Simulation manipulation. Advanced civilizations in a simulated universe might develop technologies capable of interacting with the underlying code. These technologies could allow inhabitants to alter or manipulate their reality, creating new environments, changing the laws of physics, or even editing their own experiences. By accessing the simulation's code, these civilizations could reshape their world in unprecedented ways, gaining control over their reality in ways that would be impossible in a non-simulated universe. Energy systems. In a simulated universe, energy generation and consumption could be tied directly to the system's code. Civilizations might learn to manipulate the simulation to generate limitless energy or tap into the computational resources of the system itself. This could lead to advanced energy systems that bypass the limitations of traditional physics, allowing civilizations to power their societies using the raw processing power of the simulation. Communication networks. Communication in a simulated universe could occur on multiple levels. Inhabitants might develop ways to communicate within the simulation, but they could also seek to communicate with the system's designers or even other simulations. This could lead to the development of intersimulation networks, allowing civilizations to exchange information with other simulated worlds or even with the creators of their own reality. Chapter 11. The Hyperbolic Universe. A hyperbolic universe is one where the geometry of space curves outward, creating a non-Euclidean, negatively curved space. In such a universe, the familiar rules of geometry no longer apply in the same way, and the distances between points stretch exponentially as you move farther apart. This leads to an incredibly vast, almost infinite space within a finite boundary, where gravity, motion, and the behavior of matter are drastically different from the Euclidean or spherical worlds we are familiar with. Newton's laws of motion in a hyperbolic universe. Newton's laws still apply in a hyperbolic universe, but the way objects move through space is affected by the negative curvature of the environment. First law, inertia. Objects remain in motion or at rest unless acted upon by an external force, but in a hyperbolic universe, motion is altered by the expanding distances between points. As objects move through the curved space, their trajectories can curve outward or be stretched as they travel, causing them to move along paths that appear curved or stretched out in comparison to Euclidean space. Second law, F, force equals mass times acceleration, but the way force and acceleration behave in a hyperbolic universe is affected by the curvature of space. Applying the same force in this universe may result in different accelerations compared to a Euclidean space because distances and angles are not straightforward. Objects moving through hyperbolic space may experience increasing resistance or acceleration as they travel longer distances. Third, law action-reaction. For every action, there is an equal and opposite reaction, but in a hyperbolic universe, these reactions may propagate in unexpected directions due to the curved geometry. Forces spread out more rapidly in hyperbolic space, and reactions to applied forces can ripple through space in ways that seem exaggerated compared to a flat or spherical universe. Gravitational and environmental effects. Gravity behaves uniquely in a hyperbolic universe due to the outward curvature of space. Unlike in spherical or flat universes, where gravity pulls toward a central point or evenly across a surface, gravity in a hyperbolic universe spreads outward, causing gravitational fields to behave in unexpected ways. Expanding space. In a hyperbolic universe, distances stretch outward exponentially, meaning that the space itself grows as one moves farther from a central point. This causes gravitational fields to weaken more quickly as objects move apart. Celestial bodies like stars and planets would be spaced much farther apart, and gravity's influence would diminish rapidly with distance. Gravitational effects on matter. The outward curvature of space means that objects far apart from one another experience weaker gravitational attraction than they would in a flat or spherical universe. This would lead to large, sparsely populated regions of space where gravity is weak, and matter is less likely to clump together. Celestial structures like galaxies might be more spread out, and planetary systems could have elongated, irregular orbits due to the unusual gravitational dynamics. Thermodynamics and energy distribution in a hyperbolic universe. The non-Euclidean geometry of a hyperbolic universe also affects how energy is distributed and how thermodynamic laws operate. The curved space stretches energy over larger distances, leading to different behaviors for heat transfer and entropy. First law, conservation of energy. Energy is still conserved in a hyperbolic universe, but its distribution is affected by the expanding distances. Heat and light from stars, for example, would spread out more rapidly, becoming less concentrated as they travel. This means that celestial bodies in a hyperbolic universe would need to generate much more energy to affect distant regions of space, leading to cooler, more diffuse cosmic environments. Second law, entropy. Entropy increases predictably, but the outward curvature of space in a hyperbolic universe creates regions where entropy increases faster than in a flat or spherical universe. The rapid expansion of space leads to more chaotic environments at larger scales, where the distribution of matter and energy becomes increasingly disordered as distances stretch out. Third law, absolute zero. In a hyperbolic universe, the regions farthest from the central points of gravity and energy sources would experience extremely low temperatures as energy dissipates over vast distances. These regions would approach absolute zero, creating vast cold voids where energy and matter are sparse and entropy reaches its maximum. Effects on water flow, climate, and civilization. Water, climate, and ecosystems in a hyperbolic universe are all affected by the stretching, curved nature of space. Civilizations in this universe would have to adapt to the strange and counterintuitive ways that distances and movement operate within this geometry. Water flow in ecosystems. Water in a hyperbolic universe flows along the curved surface, but the geometry of the space would cause rivers and lakes to behave differently. Water may spread out more rapidly as it flows, creating large, shallow bodies that cover vast areas. The gravitational pull on water would weaken as it moves farther from a central point, making it difficult for rivers to flow naturally toward lower areas. Civilizations may need to develop advanced technologies to manage water resources and maintain stable ecosystems. Mountains and atmosphere. The atmosphere in a hyperbolic universe would be thinner and spread out over larger areas due to the expanding distances. Weather systems would become more diffuse, with less dramatic differences in temperature or pressure between regions. Mountains and hills, if they exist, would appear to stretch outward in exaggerated ways, creating landscapes that seem to expand as one moves toward them. Civilization? Human civilizations in a hyperbolic universe would face unique challenges in adapting to the vast, stretched-out nature of space. Cities and settlements would need to be spread out across large regions with long distances between them. Transportation and communication systems would need to account for the curved space, where distances can stretch unexpectedly, making travel and resource distribution more difficult. The strange geometry of the universe would likely influence the way civilizations organize themselves, leading to unique cultural, social, and technological developments. Philosophical reflections. Infinite space and the boundaries of reality. The hyperbolic universe raises profound philosophical questions about the nature of space, infinity, and the structure of reality itself. Inhabitants of a hyperbolic universe may develop philosophies that emphasize the boundlessness of existence and the infinite possibilities of space. Philosophers in this universe may explore the idea of infinity, where space stretches endlessly outward without ever closing in on itself. The hyperbolic universe challenges the idea of finite space, offering a reality where there are always new horizons to explore and where distances can expand forever. This could lead to a worldview that emphasizes the limitless potential of existence, both physically and metaphysically. At the same time, the hyperbolic universe may inspire philosophical reflections on isolation and separation, as the expanding distances make it harder for beings and civilizations to connect with one another. The vastness of space could lead to feelings of existential loneliness, as individuals contemplate the immense, ever-expanding nature of the universe around them. Philosophical reflections on geometry and the universe. The different geometrical models of the universe, from the spherical to the hyperbolic, from flatland to simulations, open profound philosophical questions about the nature of existence, reality, and knowledge. Geometry, often thought of as an abstract branch of mathematics, can serve as a metaphor for how we understand ourselves, our place in the universe, and the larger truths of existence. The structure of space not only shapes physical reality, but also influences how civilizations and individuals conceptualize their own existence. The interconnectedness of geometry and reality. In each of the universes we've explored, the geometry of space shapes the laws of physics, the flow of time, and the very nature of life itself. Whether the universe is spherical, flat, pyramidal, or hyperbolic, its geometry affects every aspect of reality, from how objects move to how civilizations evolve. This raises fundamental questions. Is geometry an inherent property of the universe, or is it simply a way for our minds to interpret the structure of reality? Inhabitants of each universe would naturally come to accept their geometry as normal, but as they begin to explore the possibilities of other forms of space, they would start to question the universality of their experiences. A civilization in a flatland universe, for example, might find it difficult to imagine a world with depth, while inhabitants of a spherical universe might struggle to understand the concept of infinite outward expansion. Yet, each universe, in its own way, offers a valid and coherent framework for life and existence. This raises a profound philosophical question. Is reality objective, or is it shaped by the geometry and structure of the universe we inhabit? Is there one ultimate form of reality, or are all geometrical models equally valid reflections of different aspects of existence? These questions touch upon the nature of perception and the limits of human understanding. Geometry as metaphor for knowledge and exploration. Each universe can also be seen as a metaphor for different ways of knowing and exploring the world. The spherical universe, for instance, represents a world where exploration eventually leads back to where one started, each symbolizing the cyclical nature of knowledge. In contrast, the infinite plane universe suggests that knowledge and exploration can go on forever with no ultimate boundary or endpoint. These different geometries mirror different philosophical views on the nature of knowledge. Some believe that all truths are interconnected, while others hold that the search for knowledge is infinite and boundless. The fractal universe offers yet another perspective, one where knowledge is recursive and patterns repeat themselves at every level. This suggests a universe where the more one explores, the more one finds familiar structures, raising the question of whether true novelty exists or whether all of reality is just an endless repetition of the same basic forms. The role of consciousness in defining geometry. Another significant philosophical question raised by these universes is the role of consciousness in shaping our understanding of geometry. Does geometry exist independently of the observer, or does consciousness play a role in defining the structure of the universe? This question touches on long-standing debates in philosophy and physics about the nature of reality. In a simulated universe, for example, the very fabric of space might be determined by the simulation itself, meaning that the rules of geometry are not fixed, but can be changed or altered by the programmers. In such a universe, consciousness might be little more than a product of code, and the geometry of space would be a reflection of the rules set by external forces. This challenges traditional views of free will and autonomy, suggesting that consciousness may be constrained by the structure of space itself. Similarly, in a holographic universe, where everything in 3 dimensions is a projection of information encoded on a 2-dimensional surface, consciousness itself might be part of that projection. This raises the question, if reality is a projection, what is the nature of the self? Are we merely constructs of encoded information, or is there something deeper that transcends the geometry of the universe? The limits of human understanding. Exploring these various geometrical models also highlights the limits of human understanding. Each universe presents its own challenges to the way we conceptualize space, time, and reality. In a hyperbolic universe, for example, the concept of infinity becomes more than an abstract mathematical idea. It becomes a lived reality, with space stretching outward forever in all directions. In such a universe, traditional notions of distance and location break down, and the mind must adapt to a new way of thinking about space. Philosophers in each universe would have to grapple with these challenges, developing new ways of thinking to account for the unique structure of their world. In the flatland universe, philosophers might struggle to conceptualize the idea of height, just as inhabitants of a spherical universe might find it difficult to imagine an infinite plane. This suggests that our understanding of reality is shaped not just by our physical senses, but also by the geometry of the universe we inhabit. The question, then, is whether there are limits to human understanding imposed by the geometry of the universe. Can we ever fully comprehend a universe with a different geometry, or are we forever constrained by the structure of the space we live in? Unity and diversity in the structure of space. Another philosophical reflection raised by the study of geometry in the universe is the tension between unity and diversity. Each of the universes we've explored represents a different way of organizing space, yet all of them are valid, coherent models. This suggests that there may not be one correct geometry for the universe, but rather that there are multiple ways of structuring space, each with its own internal logic and coherence. This has profound implications for how we think about diversity and unity in the broader context of reality. Just as different geometrical models can coexist, each offering a unique perspective on space, so too might different cultures, philosophies, and worldviews coexist, each offering its own valid perspective on reality. The study of geometry in the universe can thus be seen as a metaphor for the diversity of human thought and experience, where no single perspective can claim absolute truth, but all contribute to a greater understanding of the whole. The search for ultimate meaning in a geometrical universe. At its core, the exploration of different geometrical universes raises questions about the search for ultimate meaning. Does the structure of space itself offer clues to the purpose of the universe, or is geometry simply a neutral framework within which life evolves? Philosophers in these universes would likely debate whether the geometry of their world is imbued with meaning, or whether it is simply an arbitrary fact of existence. In some universes, such as the pyramidal or spherical universes, the geometry of space might be seen as a reflection of deeper metaphysical truths. The pyramid, with its broad base and narrow apex, could symbolize the journey toward enlightenment or spiritual growth. The spherical universe, with its closed, cyclical nature, might suggest that all things are connected and that the universe itself is a manifestation of a greater unity. In other universes, such as the hyperbolic or fractal universes, the structure of space might suggest a more chaotic, unpredictable reality where meaning is not predetermined but must be created by conscious beings. These universes challenge the notion of a fixed, purposeful structure to the cosmos, instead emphasizing the role of individuals and civilizations in giving meaning to their existence. Conclusion: the boundaries of reality. As we have journeyed through the different universes, each shaped by its own unique geometry, we've encountered a wide array of scientific, environmental, and philosophical challenges. From the familiar spherical universe to the flat and simulated worlds, and from the intricate fractal dimensions to the boundless spaces of hyperbolic geometry, these diverse models of reality offer profound insights into the nature of existence, the structure of space, and the limits of human understanding. At the heart of this exploration is a question that transcends any single model of the universe. What is reality? Geometry, often viewed as a branch of mathematics, becomes a metaphor for how we understand the universe. It defines the rules by which space, time, and matter behave. It shapes how civilizations evolve and how individuals understand their place in the cosmos. Each geometrical universe, in its own way, forces us to rethink the assumptions we hold about reality and to confront the possibility that there may be no single, ultimate model of the universe. The power of perception and knowledge. One of the central themes that emerged from this exploration is the relationship between perception and knowledge. In each universe, the inhabitants' understanding of reality is shaped by the geometry they live within. In a flatland universe where only two dimensions exist, the very concept of height is unimaginable. In a spherical universe, distance is finite and exploration leads back to the beginning, suggesting that knowledge may also be cyclical. In a hyperbolic universe, the idea of infinity becomes tangible, challenging the limits of human comprehension. These different models of space highlight the limits of our own knowledge. Just as inhabitants of a flatland world would find it difficult to conceive of depth, so too might we find it difficult to fully comprehend the complexities of a universe with dimensions beyond our perception. Yet the exploration of these different geometrical models reveals the remarkable adaptability of consciousness. Whether it is adapting to a fractal universe with recursive patterns or grappling with the simulated nature of reality, consciousness finds ways to interpret and understand the structure of space. Reality and free will. Another recurring theme is the question of free will in relation to the structure of the universe. In a simulated universe, where the very fabric of reality is a product of programmed code, free will appears to be constrained by the rules of the system. In contrast, in a more open, infinite space, such as the hyperbolic universe, the vastness of space might offer the illusion of limitless choice, yet the very structure of the universe imposes its own constraints on movement and interaction. The structure of space seems to play a critical role in determining the extent to which individuals and civilizations can exercise free will. This raises the philosophical question of whether true autonomy exists or whether we are all bound by the geometrical limitations of the universe we inhabit. Can we ever truly break free of the boundaries imposed by space, or are our actions always in some way constrained by the structure of the cosmos? The unity of science and philosophy. Finally, this journey through geometrical universes illustrates the inseparable connection between science and philosophy. Scientific laws, such as Newton's laws of motion, play out differently in each universe, depending on the geometry of space. These variations challenge our understanding of physics, forcing us to rethink fundamental concepts like gravity, inertia, and energy. At the same time, the philosophical implications of each universe, whether it is the question of the meaning of infinity in a hyperbolic space or the metaphor of enlightenment in a pyramidal universe, invite us to consider deeper truths about existence and the human condition. The unity of science and philosophy is most apparent in the philosophical reflections on geometry. Geometry, while a tool for understanding space, also serves as a lens through which we can explore the nature of knowledge, consciousness, and reality itself. As such, each universe becomes a philosophical thought experiment, encouraging us to think beyond the physical laws and consider the greater metaphysical questions that define our place in the cosmos. A multiverse of possibilities. In the end, the different geometries of the universe remind us that there may be multiple ways to understand reality. Just as no single model of the universe can encompass all possibilities, so too might there be multiple valid perspectives on the nature of existence. Each universe we explored offers a unique way of thinking about space, time, and matter, but none of them provides a definitive answer to the question of what the universe truly is. Perhaps the ultimate lesson is that reality is not fixed or absolute. Instead, it may be shaped by the geometry of space, the nature of consciousness, and the interplay of scientific and philosophical thought. The boundaries of reality may be more flexible than we once imagined, offering a multiverse of possibilities where different geometries coexist, each offering its own perspective on the mysteries of existence. Epilogue: Beyond the Horizon of Understanding. As we reach the end of this journey, we are left standing at the edge of what we know, staring into the vast unknown beyond. The exploration of these different universes, each defined by its own unique geometry, has expanded our horizons and challenged the limits of human understanding. From spherical worlds where all paths lead back to the beginning to hyperbolic spaces where distances stretch infinitely, we have encountered a multitude of realities, each with its own rules and mysteries. Yet, despite the vastness of the universes we have explored, one truth remains: our understanding of reality is always incomplete. No single model of the universe can fully capture the complexities of existence, just as no single perspective can encompass the full range of human experience. The more we explore, the more we realize how much there is left to discover. The infinite journey. The journey through the geometries of space is, in many ways, a metaphor for the infinite nature of knowledge and discovery. Just as the inhabitants of a flatland universe cannot perceive height, so too may we be limited in our ability to comprehend the full nature of the cosmos. But this limitation is not a barrier, it is an invitation. It invites us to keep searching, to keep questioning, and to remain open to new possibilities. As civilizations evolve, they push the boundaries of their understanding, constantly redefining what is possible. In each universe, the laws of physics and the structure of space provide the framework for this exploration, but it is the drive of conscious beings, their curiosity, creativity, and desire for meaning, that propels them forward. This journey toward greater understanding is not bound by the edges of space or the constraints of geometry. It is a journey that extends beyond the physical world, into the realms of thought, imagination, and spirit. The nature of existence. At the heart of this journey lies a deeper question. What does it mean to exist? The different geometrical models of the universe suggest that existence itself is not a fixed state, but a fluid concept, shaped by the structure of space, but of the flow of time and the consciousness that perceives them. In a pyramidal universe, existence may be seen as a climb toward enlightenment, while in a hyperbolic universe it may be viewed as a boundless expansion into infinity. But regardless of the geometry, one constant remains. Existence is always a dialogue between the individual and the universe. Each of us, in our own way, is an explorer, navigating the landscape of reality, seeking to understand the world around us and our place within it. The universes we have explored in this book are not just abstract models. They are reflections of the different ways we experience reality, the different ways we search for meaning, and the different ways we find our place in the cosmos. The search for meaning. In the end, the search for meaning may be the most universal journey of all. Whether we live in a simulated universe governed by code, a flatland where height does not exist, or a fractal world of repeating patterns, the quest for purpose remains the same. It is a search that transcends space and time, uniting all beings in their desire to understand the why of existence. Each universe offers its own answers, but none provides a final absolute truth. Instead, they offer possibilities, different ways of thinking about space, time, matter, and consciousness. These possibilities, in turn, offer us new ways of thinking about ourselves, our place in the universe, and the meaning of existence. Perhaps the ultimate truth is that there is no single answer, no one path to meaning. Instead, meaning is something we create through our interactions with the universe, through our exploration of the unknown, and through our willingness to keep asking questions, even when there are no easy answers. Looking beyond. As we step back from the geometrical models we have explored, we are left with a sense of wonder. The universe, in all its complexity and mystery, is a place of endless possibility. There will always be new horizons to explore, new questions to ask, and new ways of understanding the reality we inhabit. But perhaps the most profound realization is this: the journey never truly ends. Just as the geometry of space can expand infinitely, so too can our search for knowledge, meaning, and truth. The universe, in all its forms, spherical, flat, hyperbolic, fractal, or simulated, invites us to look beyond the boundaries of what we know, to embrace the unknown, and to continue the quest for understanding wherever it may lead.